screen. நீங்க ஷேர் பண்றீங்க, நான் ஷேர் பண்ணணும் ஸ்கிரீன் கேட்குறேன். பிபிடி இன்ட்ரோடக்டரி. Good afternoon, all. I'm happy to introduce the speaker of our next session, Dr. Sudhakar Pichaimuthu. So he'll be delivering his talk on the topic Solar to Hydrogen, Opportunities and Challenges. To have a brief introduction about Dr. Sudhakar, Dr. Sudhakar Pichaimuthu is Sir Saimru II Rising Star Fellow at Specific College of Engineering, Swansea University, and leads the Multifunctional Photocatalyst and Coating Research Group at Swansea University. His current research interest is to develop semiconductor thin film-based solar light photo absorbers, quantum dot film coating, less expensive platinum-free water oxidation reduction catalyst. His research is jointly funded by the Welsh government and European Commission through the European Regional Development Fund under Sir Saimru II Rising Star Fellowship Scheme over 5 years. He was a recipient of JSPS Award from Japan Society for the Promotion of Science, Japan in 2013. Dr. Sudhakar has published more than 70 articles in peer-reviewed journals and contributed 5 book chapters. Over to Dr. Sudhakar.
Okay, thank you very much, Professor Nirmala, for nice introduction. And shall I share my screen?
Yes, sir. Yeah.
Okay, can you see my screen? Shall I go to the... One second, I will change to presentation mode. Okay. One second. Just a second. Okay, can you see my screen?
Yes.
Okay, so good evening to all in UK this morning time. First of all, I would like to thank the organizer and Professor Nirmala Grace and her team for organizing this wonderful event, even the mid of a pandemic time. And also I would like to thank all the participants to join in my talk. I know you came across a lot of hurdles like internet connection and so many personal commitments. Okay, once again, thank you. Today I'm going to deliver a lecture on solar to hydrogen. What are all the opportunities and challenges? So I'm currently working in Swansea University and leading my group, Multifunctional Photocatalyst and Coatings Group. I would like to introduce about where I come from. So in the screen, you can see the right-hand side, the United Kingdom map. So where I come from, the shadowed area, the yellow color shadowed area, it's called Wales country. So it's a part of the United Kingdom. So it's just 3 hours by train travel from the well-known city London to Swansea. And the left-hand side, you can see a beautiful panoramic view of Swansea city. Especially, we have 2 campuses, Swansea University. So this is I'm glad to share that this year we are celebrating the 100th anniversary of our university. So this is called Singleton Park campus. And you can see the another one, it's called Bay campus. It's quite very, very newborn baby. It's a 5 years old campus. So both campuses are beautifully just located on the seashore. If you have a time to visit UK, please visit our Swansea University campus. And this is another beautiful pictures of our Swansea city. And the right extreme side, you can see the beautiful photo on the seashore just behind our Swansea City Council library. At the bottom, you can see the bird eye view of our Swansea University Bay campus, where my research lab is located in this building, Central Engineering Building. And if you have time, please visit www.swansea.ac.uk. You can get more details about what are the courses available, or what are the research area, what we are doing in Swansea University campus. Okay, this is my content of the talk. So today I'm going to talk about the two important keywords. One is the solar catalyst that can be functional or operating by the solar energy, and how these solar catalysts or photoelectrocatalyst materials are applying to synthesize a green fuel. So these two keywords I'm going to talk. In a little bit, I'm going to cover what are the advantages of solar to fuel conversion, what is the fundamental principle of solar light-driven photoelectrocatalysis to hydrogen generation, how to understand the solar spectrum and the choice of material, and what are the recent progress going around the world in this area, and a little bit take-home message I conclude with my talk. So before going to my talk again, I would like to briefly introduce about my research group. So my research group mainly working on to developing a platform for synthesizing a nanomaterial and processing and analysis, mainly targeting to construct a cost-effective or less expensive solar energy conversion system towards to tackling a globally challenging issues, for instance, energy, environment, and healthcare application. So mainly our group is working in both two areas. One is the fundamentally we are developing a material synthesis and scale up in lab scale. And later on, we apply all these materials, put it in a device in a proof of concept area, and then later on we develop a at the bottom, you can see what are all the current application we are working, the solar cell, solar fuel cell, and how the photoelectrocatalyst or photocatalyst material in the environmental cleanup area. Okay, let's start my talk. So I would like to share about the very critical factor what's going around the world. It's called the globally challenging issues. In the year of 2015, United Nations identified 17 goals are very important. For example, the fighting with poverty, hunger, how to achieve a good health and well-being, so on. And all these 17 themes are very important, and we need to focus more on our research to help our humanity. Okay, so in this perspective, today I'm going to talk about the factor number. I mean the goal number 7 and goal number 13, and particularly how applying the solar catalyst materials and then try to reduce the the environmental pollutant as well as energy demand. Okay. If you see in the day-to-day market, the automobile utilization in the roadside has been increased day by day. So what happened, these enormous amount of automobile utilization, it produced a huge energy demand. If you see the global oil demand in the last 10 years, it's drastically increased. On the other hand, the huge energy consumption or the automobile utilization create a very first or uh, very bad environmental pollution in the atmosphere. If you look around the survey, especially the source of carbon dioxide emission in the environment, the transport system almost it produced 10 to 13%. Is really we have to think about how to tackle the environmental pollution as well as to how to tackle the energy demand simultaneously. So because currently we are using fossil fuel sources for our operation, but the problem is the depletion of fossil fuel sources recent decades is also another alarming us to think about the new type of energy resources. So how to tackle both energy demand and environmental pollution? So the one solution is we can adapt the solar energy because it's inexhaustible in nature, it's renewable every day, and of course it is a completely pollution free. So if we can adopt the solar energy as a accelerating force to synthesize a green fuel, we can definitely tackle the both energy demand and environmental pollution simultaneously. So why solar energy? So in the nature, you can see the every day our Earth has been receiving 2 into 10 power 14 kilowatt. Particularly, we can compare it the 10,000 times larger than energy what we consumed per day. So you can see in nature every day we are we have a plenty of excess energy from we can utilize this to utilize useful application. So before going to that, solar energy materials and then applying it in a fuel generation, so you need to understand the absorption of the solar spectrum. For example, if you study the solar light photons from the nature, if you make it in a wavelength versus, the solar light intensity, there are three color regions there. The violet one is the ultraviolet, the second one is the visible light, and then the red color shadowed area or near infrared. So this is completely give an idea how the nature solar light photon and versus intensity. Eventually, you can see the green shadowed area is a high amount of light photon intensity received from the sun, especially in the visible light region. Okay, so it clearly give an idea. If you go for any kind of solar energy application using the semiconductor, you should choose the material that semiconductor should absorb the light from the solar spectrum, particularly visible light wavelength. If I convert it into band gap energy of the semiconductor, it should be, it probably, the material should receive a high photon absorption in between 400 to 800 nanometer. And I convert into energy volt, it's maybe 1.1 to 2.8 electron volt. So whenever you start a solar energy application using the materials, so you should carefully think about to how to design or how to choose the material. So as I mentioned, so the visible light driven materials are very, very effective in a light harvesting area. So keep in this mind, so our research group, or we are working in water catalyst sun nexus. Especially, I told that the catalyst material that is more appropriate for the solar energy material. So, and also we are choosing the water as a substrate for producing the green hydrogen fuel. Of course, we are working on another pollutant degradation area. But today I'm going to talk about more on how our research group or the general ideology of creating the hydrogen fuel using the sun water catalyst. Okay. So what is the solar fuel generation, especially using the sun and semiconductor? So before go to that, I will give you a simple mechanism. In nature, you can see how the plant produce their own food using a two parameter, one is the sunlight and water. Okay, so the plants are the leaves are producing their own food using these two parameter. For example, it produces the glucose, it is a food for the plant, and it emit the oxygen. This oxygen is a byproduct. I can say this oxygen is one of the cheaper fuel. Okay, this is called natural photosynthesis process. In real world, in the laboratory, if we can replace this leaf here, in any kind of cell, the same using the sun and the solar, sunlight and the water, if we can produce the same kind of oxygen, it will be fantastic. So in the 1972, Professor Fujishima and Professor Honda, they demonstrated, they replaced instead of the natural leaf, they introduced the artificial leaf like a semiconductor, titanium dioxide, and under the sunlight irradiation, this under the small applied potential, the titanium dioxide oxidize the water into oxygen. Okay, it's very similar to the natural photosynthesis, how you develop the oxygen. So eventually, the photoelectron collected from the conduction band, it's transported to the another area. The cathode compartment produce the hydrogen fuel. Anyway, so this photoelectrocatalytic water oxidation, it's very similar to natural photosynthesis process, so-called artificial photosynthesis. So this is the first demonstration in this area. So in the year of 1972, after this work, it's a big gate is open to a wide range of materials are tested in how to achieve the solar hydrogen fuel generation from the lab, as well as how to bring to tap to market. And also, when you compare the storing the chemical energy in the solar cells to battery, the storing the chemical energy is relatively cheaper or relatively simple. So how it's feasible, I can say strongly, the hydrogen is a future economy in the world. Already the demonstration or the utilization come to the market by using the fuel cell, hydrogen fuel cell. You can see the especially Germany is a very leading partner, and Japan also working on very seriously in this area. In UK already the world first hydrogen powered buses are already operated in London. And in South Korea also recently introduced the hydrogen powered buses in the roadside. And of course, Germany already started on the hydrogen powered train in the 2016. And we are expecting UK also the similar type of train. So what these demonstration are endorse that, and definitely the hydrogen will be a big resources in the automobile or the another the transport area. So but the question is where the hydrogen will come from. Okay, so this is the big question. So as I mentioned, if you adapt the solar energy as a driving force, and if you can create or synthesizing cheaper materials, semiconductor materials, and also you can utilize the water, and then you can produce a fantastic amount of hydrogen fuel. So this will be a huge market value. Okay, now I'm going to give a short fundamental develop the hydrogen fuel using the photoelectric catalysis cell. Okay, so this is we adapted the electrochemistry, quite old electrochemistry theory. This is a simple two electrode compartment. On the left hand side is called the photoanode. This is driven by the light. And the right hand side you can see the standard cathode. It's a platinum. Okay, so in between the anode and cathode, so we fill the water and separate it with the naphthalene proton conducting membrane. So it's connected with the small applied potential like a circuit. Okay, under the sunlight. So what happened? The semiconductors are generating the photocharge carriers, photoelectron and photoholes, especially the photoholes where the valence band is higher than the 1.23 electron, 1.23 volt. Thermodynamically, these photoholes are powerful to oxidize the water into oxygen. You can see the respective reaction here. So what happened? It produces a one byproduct. It's a protons are available here. Okay. At the same time, these photoelectrons are transported to the cathode here. So next up, you can see what will happen. See, the protons are transported from the anode to cathode, and here these proton I mentioned here is a water. Okay, the protons are reduced with the help of the photoelectron and produce the molecular hydrogen gas here. So eventually, you can get the oxygen gas in the photoanode compartment and the hydrogen gas in the cathode compartment. So simultaneously, you can get both oxygen. This is called simply photoelectrocatalytic water splitting process. Okay. You can see a simple lab scale catalysis water splitting. This photo is taken in my lab. So this is you can see I told there's a photoanode compartment. The photoanode is here. This is a platinum mesh is here. It's separated with naphthalene membrane. Okay. So I'm just using the WO3 bismuth 108 photoanode here. I will show you a simple video demonstration how the hydrogen gas is generated. So under dark, you can see there is no hydrogen gas generated in the cathode compartment. Okay, I just turn on the light, see the video. Okay, you can see the bubbles are coming, started to comes on the cathode in the platinum. The photoanode is here. So as long as it is irradiated with the light, you can get the oxygen here as well as hydrogen here. But the very less amount of oxygen always producing in the anode compartment. You cannot see in the visibly in the bubbles in the anode compartment. But hydrogen you always getting higher amount, so you can see visibly the bubbles. So now you can understand how the hydrogen gas is generated in the platinum. Okay, so now I will move the another slide. So how to choose the material, in the how to put it, especially in here. Okay, is there any requirement? Of course, the semiconductor should follow the band energy structure should be favorable for the water oxidation as well as the water reduction process. For example, the two lines you can see the potential, I mean the thermodynamically, theoretically compared with the electrocatalysis, electrocatalytic water splitting versus normal hydrogen electrode. That means how the band gap structure should be appropriate for the water reduction. Okay, for example, the negative potential, for example, above the zero, okay, it will be always favorable for the proton reduction to hydrogen gas. Whenever the photoholes, I mean your valence band of the semiconductor is higher than 0.82 or somehow positive side, it always favorable for the water oxidation process. That means water to oxygen. So keep in mind, so the band gap energy structure or the position is very, very important in view of the thermodynamical point of water oxidation and water reduction. Suppose if my material valency band is favorable for water oxidation, unfortunately my conduction band is lesser than the required potential of water reduction. So in this case, you can choose another very good partner material. That material should be a good water reduction potential. I mean the energy band gap, even though that material have some problem with water oxidation. You can make it A plus B. So what happened, the excess amount in a oxide, OEP material and HEP material, you can add some kind of chemical that should be conducting a reduction and oxidation artificially. So it suck or the scavenging the excess carriers and make it neutral. Okay. So this is the one of the, alternatively you can choose the material even if you have a problem. Suppose if you doesn't want to introduce any kind of chemical in the water electrolyte, so you can introduce another semiconductor material in between the material A and B. So this interfacial material or the solid state electron mediator can neutralize the excess electron and excess holes from the first and second material. Okay, so there are plenty of options you can use. This is a kind of called jet stream charge transfer. Okay, I'm simply summarize again all the process. You can see the required potential window for water splitting, how it make a water oxidation and water reduction. Okay, the TiO2 is a well-known material studied in water photoelectrocatalytic water splitting research area. This is absolutely fantastic material for favoring the water oxidation because it's a very high positive valency band. But the platinum here, it is a dark catalyst. So it can be, satisfied both water oxidation and water reduction. That's a different theory. But I want to compare, whenever the valence band materials are higher than the required potential of 1.2 volt, this is absolutely fine for water oxidation. In the case of the conduction band is always higher than the required potential above zero, is always favorable for water reduction to hydrogen. So this is the second parameter, keep in mind. Okay, so how I can study the material? So you can follow the electrocatalysis theory simply. So put it in a photoelectrochemical cell and apply a small potential in the circuit and see any kind of current generation in the circuit. Okay, in the dark, no. That means no photocatalysis, no current generation or no water splitting process happening under the dark condition. So if I apply the small potential after some time, for example, 0.3 volt, and then it start to give a small amount of photocurrent generation in the circuit. Okay, so it goes up, and after some time it start to saturate it. Okay, so this point it will give you the idea of the water oxidation at anode or the water reduction at cathode. It give a two meaning. Okay, so when I make a small modification in the material, I mean, especially in the photoanode material, for example, I dope a small amount of gadolinium, the photocurrent generation is slightly or markedly increased from here to there. That means the water oxidation performance is improved after doping. So here, the current increment give you the idea, whenever you do the modification, the enhanced water oxidation or correspondingly the water reduction. So from using the JV plot, you can characterize your photoelectrocatalytic water splitting process. On the other hand, of course, it is a varying applied potential. You can keep it a constant applied potential. You can use the chronoamperometric studies. That means the time versus current density. So it should be ideally it should be same, but there may be the different type of corrosion. So it may be start to reduce. Okay. Anyway, so you can, for example, in this point, you can get idea what is the current density produced. Okay. So these two plots give you an idea how much current density is produced in your photoelectrochemical cell. Another way, you can collect the hydrogen gas from your cell and then put it in a gas chromatography. It will give you the idea of how much hydrogen evolution from your liquid. Okay. So I'm going to, so this is the how to calculate the solar to hydrogen efficiency. This is the benchmarking parameter, keep in mind. So there are two ways you can calculate the photo current density. I mean, the how much current is produced in your JV plot. And this will give you the overall idea about the solar to hydrogen efficiency. Suppose if you are dealing with the hydrogen fuel, so this is another formula. So anyway, both formulas are accepted, So as long as if you have a high solar to hydrogen efficiency, particularly in the more than 10%, okay, so it will be a good material. So the entire world, the research is going how to achieve the solar to hydrogen efficiency 10% or above the 10%, okay. So I will go another important key factors. What are the problems coming in your whenever your semiconductor electrode put it inside the electrolyte? Okay, it's called electrode-electrolyte interfaces, especially under light radiation. The first problem always the semiconductor have, as I mentioned, the photo charge generation, photoelectrons and photoholes. The problem is itself recombine itself. Okay, it's called bulk recombination. It's like a tug of war between the photoelectron and photoholes. So as long as it's generated, you should separate the photocharge carriers. The second problem is the surface defect. It may be oxygen deficiency or sulfur deficiency or whatever it may be. The surface defects is always happen on the interfaces. These always make a recombination of charges, and it will affect the hydrogen generation efficiency. And of course, your material should show a high light harvesting. The long light radiation, the material goes the photo corrosion or chemical corrosion. So you should keep in mind how to tackle all these problems whenever you introduce the electrode and electrolyte interfaces under light irradiation. So overall, I summarize here. There are different strategies are going in a photoelectrocatalytic solar to hydrogen fuel generation. So one is the material aspect, how to enhance the light harvesting and assembling co-catalyst materials, and of course you can introduce the platinum-free cathode materials, and how to enhance the photoelectrocatalytic process, for example, to enhance the high charge how to make a effective charge transport. Of course, recent days, the work is significant work is going on self-driven photoelectrocatalytic system. For example, without applied potential, how you can drive your photoelectrochemical cell. So you can consume or save a huge amount of energy. And of course, if you are introducing the photovoltaic system in the circuit, of course, it is a you can eventually increase the solar to hydrogen fuel efficiency. So this will be a futuristic research area is going around the world. And of course, the sustainability is very, very important. There will be another possibility. You can passivate your layers, your photo anode or photo cathode with amorphous metal oxide or any other suitable polymer layers. You can protect your electrodes, against the photo corrosion or chemical corrosion. And another work is going. So instead of using the pure water, it may affect the food chain. So instead, you can introduce the biomass-based or water pollutant or seawater. These may be alternative feedstock. You can utilize it, and you can develop the hydrogen fuel generation. So I don't have a time. So if you have a time, please take a look of the refer this review. So how the solar to hydrogen efficiency with respect to different wavelength, especially how it will influence on, affected by the apparent quantum yield. Okay, so there are so many recent progress going around the world. I don't have time. So this is a three-dimensional structure we demonstrated, both satisfying the effective light harvesting as well as the charge transport. And of course, introducing the graphene flakes in titanium dioxide structure. Here these additionally add graphene oxide material. It make a good charge separation, and eventually we are getting the high charge photoelectron collection in the photoanode. The circuit. Okay. And of course, this is one of the very good review how the co-catalyst materials or thermodynamically, reduce the thermodynamically reduce the energy consumption. Okay, so this is another review reported by Professor Conley. So please take a look on this review, especially how the applied potential, water splitting potential is reduced from after introducing the co-catalyst on the semiconductor surface. Of course, you can. I'm sorry, I didn't mention Professor Kamat's article. There are so many articles in his group page. You can please go through it, and I don't have time. So the another good work I would like to mention how the solar cells are in situ, like a monolithic structure, introduced in situ. Okay, the water oxidation or water oxidation catalyst materials introduced in both side or any one side, how it will drastically improve the solar light absorption as well as the the water catalyst water splitting reaction. And of course, recently research have started to testing how to apply the perovskite material in this in water oxidation system. But problem is perovskite is not stable in in the humidity or in the water. So they try to apply to seal the perovskite material with carbon or any other suitable material. So this also it's going next direction in this area. So of course, we recently demonstrated how the amorphous metal oxide layer coated on the very serious corrosive cadmium selenium layer, and it make a sustainable hydrogen generation. Okay, I think almost we are across that time. So I would like to mention about the few points again. Solar energy material, especially absorber as well as catalyst or promising candidate. It's both tackling environmental cleanup as well as the energy demand, as I mentioned, solar fuel generation. So very important understanding the energetic structure is very important. How this will be favorable for either water oxidation or water reduction. So the understanding the energy structure is very important, and of course the stability of the photoelectric catalyst or solar catalyst material before and after reaction is very important. So we need to study and show it characterization methods. Okay, and of course there are few points to keep in mind to design the uh, effective reactor design. Okay, so without no gas leaking or whatever it may be, and also charge transfer characteristics, and to study it using the appropriate methods like a transient absorption spectroscopy or electrochemical impedance spectroscopy, because the charge separation or the how the charge transfer characteristics inside even the semiconductor to the charge collector is very important. And of course, we need to evaluate the apparent quantum yield using the IPC analysis. Okay, and of course the taxonomy. That means you have to calculate the how much cost involved in from the laboratory. The complete your material from your material synthesized to the final prototype demonstration. Okay. So now, yeah, as I mentioned, you can introduce any kind of a renewable energy system in the circuit, like a solar photovoltaics or wind energy. All these kind of direct current, the power generation will help you to separate the charge separation, as well as it can increase your solar to hydrogen efficiency drastically. Of course, we need to think about how to utilize the wastewater or any kind of waste feedstock instead of pure water. Okay, thank you very much. And of course, I would like to thank all my collaborators, as well as my mentors, Professor James Tarrant and Professor Fujishima, and of course my Professor Dave, as well as Professor Tristan from Swansea University. Thank you very much.
Thank you, Dr. Sudhakar, for your interesting speech. I would swiftly consolidate two questions from the participants. Question one is, in upcoming future, there is going to be scarcity of pure water. Should we consider splitting seawater? In that case, many other ions in seawater will create problems. What's your view?
Okay, I think a few research articles already demonstrated, the simulated seawater. Of course, I understand seawater consume a lot of unnecessary ions. So I think it needs some kind of three-step, purifying the seawater. And of course, the another big problem in seawater, it is a strong, acidic condition. It corrode your electrode. So definitely it might need a proper passivation layer. So if you have enough protection layer of your either photon or the photocathode, definitely you can demonstrate. Yeah, seawater will be a good feedstock. But of course, you need a free, the filtration process.
Okay. And the next question is, what would be the effect of water splitting with single crystal and polycrystalline material?
Okay, that's a classical question. I think single crystal, of course, it is always you can have a very high charge separation, okay, because the defects are very, very less when you compare to the polycrystalline. But problem is you're synthesizing a single crystal is very, very difficult, compared to polycrystalline. Of course, single crystal always best, but it's very tedious and very complex. But instead, polycrystalline are it's very easy, So, but we need to take some step how to increase the efficiency or the charge separation, whatever it may be in polycrystalline material. So, in my point of view, polycrystalline is much, much better. But theoretically, of course, single crystal is ideal for water splitting.
Okay, thank you, Dr. Sudhakar.
I think the questions are done. Just a minute.
Is it okay?
Yeah, it's fine. So thank you, Dr. Sudhakar. Thanks again for joining the session. It was very interesting session on photoelectrocatalysis. Thanks again.
Thank you, Professor Nirmala. Dr. Nirmala.
Thank you.
Thank you so much. Yeah,
Bye.
thank you.
Bye.
Bye.